Okay, hello. Welcome to Note Set 11A. So originally I had these just as one big note set, and I decided to split them up into A and B to make the videos not quite as long. I can't promise that I'll always do that, but it made sense here. So we're going to talk about inverse matrices, and this would actually be the final piece that we would need if we were going to do a proof of the fact that elimination doesn't change, well, elimination and permutation doesn't change the solution to the equation. Although we're not going to do that, we after this we would have the material necessary to do that. So this is material coming out of section 2.5. So I encourage you to read the textbook because it does go into some details that we kind of gloss over here. So early in the course we showed you a list of important dates in the history of linear algebra, and I find it very interesting that it was quite a ways into the history before the concept of an inverse matrix was developed. So a lot of stuff was done before the concept of inverting a matrix arose, and you'll see that we haven't really talked about a lot of the things that happened before that. So we've been talking about Gauss elimination. We've not really talked about determinant, although we did refer to that. We certainly haven't talked about eigenvalues, and we've been talking about matrices and been using the term matrix. So I really think that this concept of inverse matrix was probably there, because they were definitely kind of solving these things. And I find it interesting that similar matrix was used here, but according to this list, we hadn't used the term matrix yet. So this is a little bit debatable. This was just some list that was available. I think maybe from the textbook. I can't actually remember where I got this. But anyway, the point is that we're hitting one of these big ideas here. So the inverse matrix is really a big, very, very big idea in concepts of matrices and linear algebra. And once we introduce it here, we'll be seeing it throughout the course. So we'll kind of motivate the idea here, and we're limiting ourselves to talking about square matrices. So technically, the way we're defining inverse matrix here is only applicable to square matrices. And so what we're looking for, you give me a square matrix, I'm looking for another matrix that has the same size as the given matrix A, and we'll call it the inverse matrix, A inverse. So this little superscript here we read as inverse. And in order for it to be the inverse matrix of A, it has to satisfy this. A inverse times A has to give us back the identity matrix. And actually it has to work the other way too. I don't know if I show that. Yeah, I don't really show that. I should really say and A times A inverse also equals the identity matrix. So you do need it to do it both directions. I think actually if you restrict yourself to square matrices, you can show that having one of these gives you the other one. But you'll see in some books that they'll say given a matrix A, and they won't necessarily say that it's square. The inverse of it is a matrix that has both of these conditions met. And then from that, they probably then go on to show that this is true only when A is square. So anyway, we're not going to fuss over that too much. Now, the cool thing is that, and the reason that we're interested in this, remember, we've got this AX sitting on one side. If we hit that from the left with the A inverse matrix, this reduces to the identity matrix. The identity matrix times X gives us X. And so that breaks free the X. And so if we look at this on applied to the equation here, if we left multiply by A inverse on both sides of the equation, we get something that looks like that. And if A inverse really is the inverse, then this becomes the identity matrix and goes away, and we've isolated X. And so our solution is X is equal to A inverse times B. So the good news is that we now have a way to easily solve this equation without really going through the elimination. So that's not saying that the elimination approach is no good anymore. Sometimes that's what you need, and it's a necessary, important concept to know. But other times we want to talk about, like, hey, there's this new matrix, A inverse, and if I find it and then I left multiply B, bang, I've got the solution to the equation. Now, that's the good news. The bad news is, for some problems, A inverse might not exist, but we've already saw that there were problems with the elimination, right? There was a scenario where we had no solution, and there was a scenario where we had infinitely many solutions. Both of those scenarios are in the case where A inverse doesn't really exist. So this is really not all that bad news. So if we have an AX equal to B, and there is a unique single solution X to that equation, this approach, finding the inverse, multiplying the inverse by B, will find it. And later on in the course, we'll talk more about solutions in these other cases. And we'll even talk about setting up equations where A is not square. But that's much further down the road. And I'd like to point out that, what we're really doing here, if we think about backing this up to the scalar case. So suppose we have just a number A times a single variable X is equal to some other number B. So A and B here are just scalars. So this is just a regular old proportionality equation. And we know A, we know B, and we're trying to find X. What would we do? Well, we would think about dividing both sides by A, and that would give us our solution, because on this side the A's cancel, and we've isolated X. Well, think about this. We can think about 1 over A. So we could say we've got AX is equal to B. I'm going to leave a little gap there. You'll see why in just a minute. AX is equal to B. If I multiply by 1 over A there, and I multiply by 1 over A there, again, I see that 1 over A times A gives me 1. Remember, 1 is kind of the scalar version of the identity matrix, or better to say it the other way around. The identity matrix is the matrix version of the scalar 1. And so I've isolated X to give me the solution. And so the solution is 1 over A times B. Well, we could just as easily say, well, A inverse. What does A inverse mean? Well, in the scalar world, it just means the reciprocal of A. And does that always exist? Well, it'll exist anytime A is not equal to 0. So, if we had 0x is equal to B, there's no solution, when B is not equal to 0. So it's interesting to always try to tie these things back to the more restrictive or more normal scenarios for the scalar equations, and kind of make sense of why we're doing what we're doing. So in the scalar case, it's easy. You just divide by A. Now in the matrix case, there's no concept of dividing by a matrix. We have to find the inverse matrix, and then we multiply from the left, or I sometimes refer to multiplying from the left as pre-multiplying and multiplying from the right as post-multiplying. Anyway, this is tying this back to things that you should, that should help you make sense of this. So here's our definition. Aha, here, I did get it in the notes here. I'm writing it both ways. So matrix A is invertible if there exists a matrix which we call A inverse, such that left multiplying by A inverse gives us the identity, and right multiplying by A inverse gives us the identity. Has to work both ways. So when, in the real world, when we end up with a square matrix, that's one of the first things we're usually asking about that square matrix. Is it invertible? Because if it's invertible, then the equations that involve that matrix will be solvable. Now, to actually figure out if A is invertible, well, one thing we could do is, in the next set of notes, we'll learn how to actually compute the inverse. And so one way to find out is it invertible is to actually try to compute it. And if it works, then we say, yes, it is invertible. If it fails, if that computation fails, and we'll see what we mean by that failing, it'll be similar to a failure in doing elimination. But if it fails, then we'll say, aha, A inverse is not invertible. But that could be a lot of work to just, ultimately find out, no, it doesn't work. And so there are some other ways that we can assess whether A is invertible or not without actually trying to compute it. And lots of times we may be talking about a matrix A that we don't actually have some numerical values for it, but we can express it in terms of some other things, also maybe not numerical. As engineers, we have to deal with potential numbers, right? So we represent those as variable things that we as engineers will strive to ultimately assign some values to them, but we're trying to design our system. We may be trying to choose or construct an A that will be invertible. And so you can't always just rely on, well, my computer will compute it. You often, as engineers, trying to construct or devise or design something, we need to be able to think through, if I do it this way, I don't know what the actual numbers will come out to be, but this is my process, and my process will give me an invertible A. Well, then, there you go. You're all set. As I've been trying to stress all throughout this course, it's not about getting the numbers. It's about having the insight as to how this all works. And I'm going to continue drilling that into your heads as we go through this course. So I do want to take just one slide aside. Oh, I like that. One slide aside. And talk about the concepts from math and logic, the field of logic, that are if, only if, and if and only if. Now, chances are you saw this in your calc class. Chances are it may not have sunk in. But these concepts are important enough that it's worth taking a little bit of time talking about them. Because we'll throw them around throughout the rest of the course. These are much more important when you're dealing with proving, like in a math course where you're proving theorems. But it's also pretty important if you're a consumer of math to know when things are guaranteed and when things aren't guaranteed. So this kind of thinking can help you in your engineering designs, and it can also help you in your regular life, believe it or not. So let's talk a little bit about this, and I've put it in a non-mathematical setting. So let's say that we say some guy Pete will like the animal if it is a dog. What this is telling us is you look at the animal, you see it's a dog, you immediately know Pete will like this animal. So Pete will like the animal if it is a dog. So in other words, Pete will like any animal that is a dog. And every dog, he'll like every dog. If it's a dog, he's going to like it. But that doesn't mean that Pete won't like a cat. So there could be other animals that Pete also likes. So you can't say, Pete likes this animal, therefore it must be a dog. Can't do that if the only statement you know is Pete will like the animal if it is a dog. So another set of terminology used for this if, so this is the if construction. Pete will like the animal if it is a dog. We're saying that being a dog is a sufficient condition for Pete to like it. Is it a dog? Yes, that's sufficient for us to say Pete will like it. But it's not a necessary condition. So here's a rabbit. Well, it's not a dog, but being a dog is not a necessary condition for Pete to like it. Pete might like this rabbit. We don't know. So that's the if, and that's sufficient. So the if is a sufficient condition. Now let's talk about Susan. Susan will like the animal only if it is a dog. So as soon as you know Susan likes this animal, you know that the animal is a dog. See, we didn't know that for Pete. Pete likes the animal. Could be a dog, could be a cat, could be a rabbit. I don't know. Just because you know that Pete likes it, you don't know what kind of animal it is. But with Susan, you know Susan likes it. It's a dog because she will like the animal only if it is a dog. So the only kind of animal that Susan will ever like is a dog. She hates rabbits, she hates cats, horses, everything. Everything she hates except for dogs. But that doesn't mean necessarily that Susan likes all dogs. If she likes it, you know it's a dog. But if it's a dog, you don't know if she's going to like it. So it doesn't go the other way. So for Pete, it didn't go the other way. If I tried to switch this arrow around and say, well, Pete likes it, therefore it must be a dog. Not true. Not for Pete. Well, for Susan, we know if she likes it, it's a dog. But if we ask, it's a dog, does she like it? Don't know. And so this is what's known as a necessary condition. Being a dog is necessary for Susan to like it. But it's not a sufficient condition. Being a dog is just not sufficient to say that Susan likes it. So we've got if, which is a sufficient condition. We've got only if, which is a necessary condition. And then, clearly, if and only if combines them together. So now we've got Jake. Jake will like the animal if and only if it is a dog. So if it's a dog, he's going to like it. If it's anything else, he's not going to like it. That's the only if part. So Jake likes all dogs, but no other animal. No other kind of animal. That's what this says. And we have a double going arrow here. So usually this arrow, doesn't have the little gap there, but I couldn't find a double arrow, so I had to use two arrows next to each other. So this is going both ways. If you know that here's an animal and Jake likes it, you know it is a dog. And if here's a dog, you know that Jake is going to like it. It goes both ways. So being a dog is both necessary and sufficient condition for Jake to like it. It's necessary because if it's not a dog, he ain't going to like it. And it's sufficient because if he likes it, it's a dog. Okay? And if it's a dog, he's going to like it. So a sufficient condition each way. Yeah, I said that wrong the first time. The necessary part is If he likes it, it's going to be a dog. It's necessary for it to be a dog for him to like it. Sufficient is it's a dog. Therefore, he's going to like it because being a dog is sufficient for him to like it. So that's an important concept, and we'll be throwing those things around. Less so than if we were in a proof-based linear algebra class, but they'll pop up every once in a while. All right, so we've got this idea of A inverse nailed down, and we're going to talk about 6 characteristics or 6 things that we can state about it. And here's that if and only if. So sometimes we abbreviate if and only if as IFF. So that's not really a typo. That is just an abbreviation for if and only if. And I'm just pointing out again over here that if and only if goes both ways. We say this if and only if that. That means this is true if that is true, and it means the other way true too. That is true if this is true. So it goes both ways. So the inverse exists if and only if elimination produces n pivots after elimination. So remember, pivots cannot be 0. So as soon as we get a 0 along the diagonal, that we can't fix through permutation matrix, then we've failed this condition, and no inverse exists. So remember, this is if and only if. So we can check if we have n pivots, none of them are 0, then the inverse exists. The other way around, if somehow else we know that the inverse exists, maybe we've computed it, we have it, then we know that elimination will produce n pivots. So this n this is an n by n matrix. I guess we should say that up here. Okay, so it's pretty easy to see the reason behind this, that since elimination solves this, when you're done, you effectively end up having solved x, but you haven't really explicitly used the inverse to do that, but you've showed that this is uniquely solvable, and we just talked about how if the inverse exists, then we're getting a unique solution to this. So here's another note about A inverse. The matrix A cannot have 2 different inverses. So in other words, A inverse is unique. So remember, think about that 1 over A, right? You give me a number A, I look at its reciprocal or its inverse, 1 over A, that's just one number. They can't have 2 different numbers. But remember, weird and wacky things happen when we go over into the matrix world, right? In the scalar world, scalar A times scalar B is equal to scalar B times scalar A, but we saw that commutativity of multiplication doesn't carry over into matrices. So, who's to say that in the matrix world we couldn't have 2 different inverses? Well, let's see. Let's suppose that's not true, that we could have 2 different inverses. So suppose we've got B, and that's an inverse of A, and suppose we've got C, which is also an inverse of A, and suppose they are not equal to each other. They're different. Let's see what happens. Well, since B and C are both inverses of A, we showed that the inverse has to left multiply A to give the identity. So since B is an inverse of A, I multiply it from the left, and I must get the identity matrix. But C is also an inverse of A. I suppose that anyway. So if C is an inverse of A, if I right multiply it into A, I must also get the identity matrix. Okay, good. But we know that by the commutativity, associativity of matrix multiplication, it doesn't matter what order we do this, so B times the product AC must be equal to the product BA times C. So we know that is true. But what do we know, right? We know that AC gives us the identity matrix, so this becomes the identity matrix. which is what we have here. And on the other side, we know that BA becomes the identity matrix. So this becomes the identity matrix. So there it is. And then we know that B times A gives us B, or I'm sorry, B times I gives us B, because that's what the identity matrix does. And I times C gives us C. And we've shown that B must be equal to C. So we suppose that we had two different ones, but since they must both be inverses, the action of them acting like inverses requires that they be equal to each other. So we've just proved this. Aha, I told you we weren't going to do any proofs. Well, we just did one. And I didn't put theorem proof, and maybe it was less painful that way. A little less painful if I don't spring it on you as theorem followed by proof. But you know what? Proving stuff is what engineers do. We're really interested in, if I do this, will I get the response or the kind of behavior from my circuit or my system that I want? To ensure that that will happen, so that it's not just a crapshoot. We are kind of proving things. We're proving that if I do this, then that will happen. That's kind of like a mathematical proof. So don't let anyone tell you that engineers really don't need to know about how to do mathematical proofs, because we really are kind of doing them on a day-to-day basis. We just may not do them as formally as might be done in a math class. Okay, note number 3. If A is invertible, the one and only solution to our AX equal to B is X is equal to A inverse times B. So the one and only solution. So the one means there is a solution, so it's solvable, and it's unique. There isn't any other solution. Remember, we already said A inverse is unique. That's note 2. There's not two different things that work as the inverse. So that gives us the only part. And the fact that we're saying that if A is invertible, then the inverse exists. So there is at least one. So this tells us that this gives us a unique solution when A is invertible. So remember, we said, hey, when somebody hands you a square matrix, the thing that you first want to ask is it invertible? Because as soon as we know that it's invertible, we know, yes, there will be a unique solution to this. And as engineers, finding unique solutions is kind of a good thing to do. Note number 4. Suppose there is a non-zero vector x that when we map it with A, so here we're not looking for what is the solution. We're saying I pick some vector x and I shove it into A from the right. And suppose that x gives me 0, the 0 vector. And suppose that x was not 0. I mean, clearly I can get 0 if I pick x to be the 0 vector. Just set all the elements to 0. And we know that now we're forming a linear combination of all the columns of A, but the weights on all those terms are 0. So we have 0 times column 1 plus 0 times column 2, blah, 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 blah. Obviously, that's going to add up to 0. But here we're saying x is not 0. So at least one of the terms is not 0. But all of them might be non-zero. So if there's some non-zero vector x that maps into 0 through the action of A, then A cannot have an inverse. So think about it from our scalar point of view, right? Suppose we had A times X is equal to 0. So this is just a scalar equation. And I tell you that this happens when that X is not equal to 0. Well, what can I get? I know that, how can I get 0? A must be equal to 0, and therefore I cannot form 1 over A. This is that same thing, except in the matrix world. It's a little more interesting, a little more colorful, a little bit more interesting flavor. So no invertible matrix can bring 0 back to x, right? That's really what this is saying. I take, if I had this case, then I could get back this x by saying x is equal to A inverse times the 0 vector. But remember, this is forming linear combinations of the columns of A inverse. But the weights on those columns are all 0. So it's saying 0 times a column plus 0 times a column. And so those all have to add up to 0. But we said that x was non-zero. So we can't have this. So lots of interesting stuff here. And that's a big idea. So the zero matrix is not invertible. So, I mean, that's not the only matrix that causes us problems. But certainly all zeros in the matrix A will cause it to be not invertible. But unlike in the scalar case where, we had AX is equal to 0, for the scalar case, the only situation that's bad is when A is equal to 0. But in the matrix case, certainly the zero matrix case is bad, but there are actually other matrices A that are not all zeros for which this condition can exist, and A would not have an inverse. So if A is invertible, then flipping this around the other way around. So suppose I know that A is invertible, then AX equal to 0, the only solution to that is X is equal to the 0 vector. Note number 5. So all the other ones were very general things. This is just a very specific thing. Suppose we're talking about a 2 by 2 matrix. Here's an easy way to check if it's invertible. So our matrix has elements A, B, C, and D. So we're populating it in this zigzag shape going across a row and then zigzag down to the next row. So A, B, C, D. If this quantity, AD minus BC, and so I'll give you a little way to remember that. So AD is this diagonal's product. BC is this diagonal's product. So you go this product minus that product. If that result is not 0, then the matrix is invertible, and the inverse is given by this. So notice that quantity shows up in the denominator. So if it's not 0, we can do that division. And notice the structure of how we populate this matrix. We have D going here. We have A going here. So those on this diagonal flip, and then on the other diagonal, they get negated. And I would encourage you to, just for arbitrary values, leave it as A, B, C, and D. Do this multiplication. Take this thing and multiply it by the A, which is this thing, without the inverse. And verify that you get the identity matrix. That would be an excellent little exercise for you to do. And it turns out, as we look ahead, when we get into Chapter 5, for 2 by 2 matrix, we'll see that this quantity is called the determinant of that matrix. And for other larger, 3 by 3s, 4 by 4s, and so on, there will be something called the determinant, but it won't be this simple. And we'll see that for a general matrix, if the determinant is not 0, then the matrix is invertible. And to be honest, that's actually an if and only if. So a matrix is invertible if and only if its determinant is not 0. So here's a matrix, 2 by 2. Is it invertible? And the answer is no. So I would encourage you to stop the video now and see if you can apply concepts that we just talked about to check that, and then come back. All right. Well, from note 5, if we form that determinant thing, AD minus BC. So AD is 1 times 2, minus BC is 1 times 2, and so we get 2 minus 2 is equal to 0. The determinant was equal to 0, so that fails. So it is not invertible. But let's also look at this just looking ahead. Come on. I don't know why this does that. There we go. Oh, my goodness. Let's also look at this. Look at this. 1, 1 and 2, 2. Well, we see that we have the same ratio, 1 to 2, same ratio, 1 to 2. So we've seen this kind of issue before, and in fact, if we were to try to do elimination on this matrix A, we would find out that we don't have 2 pivots. So we have the first pivot, which is the 1 in the upper left-hand corner. But then once we do that first elimination, we'll end up getting 0, 0 in the bottom, and so we would not have a pivot on the second row. And so that leads us to, well, I'm not quite there yet. We can also check with note number 4. There is an x vector that when we multiply A by that x vector, so when we do AX, it will end up being equal to 0. And you can see how that will work. So put our x vector here, put a 2 here, put a -1 here. Now do our trick for multiplication. So it would be 2 times 1 minus 1 times 2 gives us 0. Then we'll have 2 times 1 plus a -1 times 2 gives us 0. So our resulting vector is 0. And so fail. Remember, note 4 said that it's invertible only if the only x that maps into 0 is 0. And then from note 1, this is what I was starting to get at, we should have 2 pivots. But because of this 1, 2, 1, 2, we don't get a pivot in the second row, and so that's also a fail. And so also notice that the columns here, and we'll talk more about this later, the columns here are linearly dependent. So if we were to look on our axis here, say this is x1, x1, and this is x2, our columns, well, we've got a 1, 1, and we've got a 2, 2. So they lie on the same line. So they are two-dimensional vectors that are collinear, therefore they are linearly dependent. So we haven't gotten there yet, but we'll get there. If the columns of the matrix A are linearly dependent, then the matrix is not invertible. Note 6. Diagonal matrix has an inverse provided that none of the diagonal entries are 0. So here's an A matrix. When we write it like this, we are evoking that it's a diagonal matrix. So all the elements up here would all be 0, and all the elements down here would all be 0. So we only have non-zero elements on the diagonal. So those are the diagonal entries. And if all of those are non-zero, then the inverse is just the reciprocal, a diagonal matrix with reciprocals down it. And we would again have zeros out here and zeros out here. So here's another case where I would say, don't put in real numbers, just write it as these variables. Train yourself to start working with arbitrary variables, because you're going to have to be doing that. Junior year, just around the corner, and you're going to have to be using variables in your coursework, because that's what engineers do. We don't work with numbers all the time. We're trying to figure out what the numbers need to be, but we don't know what they are ahead of time. So we have to work our problems with variables, and then at the end figure out what those variables end up needing to be to meet certain conditions. So work this problem. Take this A times this A inverse and work it out with these arbitrary D1s through DNs and show that this does indeed work and gives you the identity matrix. All right, inverse of a product AB. So remember, first of all, we said that there's no guarantee that we can even multiply A times B. But here we're going to assume that we can. And we'll motivate this first, again, by dipping back into the world of scalars. So suppose I've got some number A and some number B, and I form their product, AB. And so we know that this number is invertible. So in other words, I can take its reciprocal. If and only if the A and B are separately invertible. So in other words, AB, the product AB, is not equal to 0 if and only if neither A nor B is equal to 0. And there's a simple example. And so AB is equal to -9, and its inverse is 1 over -9. And just in passing, A plus B in this case is not invertible. And we'll have the similar kind of thing in the matrix world. AB may be invertible, but A plus B may not be invertible. So kind of an interesting world. So here we say, if matrices A and B are each individually invertible, then so is their product AB. So this is just an obvious generalization of what you know for the scalars. But the interesting thing is that for the scalar case, it doesn't matter which way I multiply those, 1/3 times -1/3, or -1/3 times 1/3, both give me 1 over -9. But here it will be important. So AB, in that order, take the inverse of their product, turns out to be B inverse first, then A inverse. And we're assuming here that A and B have the same size, because first of all, we are limiting ourselves to square matrices. You'll find out that if they're square and you can multiply them, then they must be the same size. So in reality, we don't even really have to assume that they are the same size. Now, notice that when we invert the product, we get their individual inverses, but in the reversed order. So that's kind of interesting, and we'll see in just a little bit why that is. So I'm just restating what we had, just so we have it there to see. And now we want to explore, why is the order reversed? So if I tell you that I have the inverse of AB, and I'm telling you that it's this, B inverse times A inverse, then we, based on what we already know, we know the following needs to be true. So if this really is the inverse of AB, if I multiply from the right into AB, I better get the identity matrix, right? Okay, so let's see what ends up happening here. So AB times B inverse A inverse, we've got a bunch of parentheses there, but remember, associativity of multiplication allows us to move those parentheses around, or in fact completely eliminate them, and then put them back in some way. So notice that B and B inverse are snuggled up right next to each other, and so here they act together to give the identity matrix. So now you're starting to see why they have to be in reverse order, so that when we multiply from the right, the B and the B inverse snuggle up. But what if we did it the other way? Because remember, it has to go both ways. If we took this and moved it over here, then what do we get? We get A snuggling up next to A inverse, and those will work together to give me the identity. So let's keep going with this. This becomes the identity, and then A times the identity is just A. And so we get A times A inverse, but A inverse is the inverse of A, duh, right? And so then we get the identity. And so we've just proved that this is definitely true. And you can do it the other way too. Multiply from the left by B inverse A inverse, and you can go through the same steps. And if we have three or more matrices in a row, so we've got A times B times C, so all of them are square matrices, all of them are individually invertible. The inverse is in the opposite direction, so A inverse, B inverse, C inverse, and we can do 4, 5, it doesn't matter how many we do. So this is kind of a basic rule of mathematics that gets lost in the scalar world because multiplication is commutative in the scalar world. But in the world where commutativity doesn't hold, it's important to remember that inverses come in the reverse order that the originals come in. And I love this example. So this was Professor Zhang, or I don't know if it was his idea or whether he took it out of the book or somewhere else, but this is a very nice way to think about it. So if you put on socks, then shoes, when you're done, when you're going to take things off, which is kind of the inverse operation, what do you take off first? Shoes, right? Then socks. Now, of course, I don't know if you have seen, there's a very funny video from a very old TV show called All in the Family. And there's two characters in that show that argue whether, when you're putting on your socks and shoes, whether you should go sock, sock, shoe, shoe, or sock, shoe. And they each have brilliant arguments for why each of their ideas is correct. And, in my mind, it shows how people can get ingrained into one way of thinking. And, even though there are other ways to think, they get ingrained into their way of thinking, and they will argue vehemently that their way is the right way. Oftentimes, just because of pre-established, ideologies. But anyway, this is math that we're talking about, and there's not ideologies in math. So in math, inverses come in reverse order. End of story. In the next set of notes, we'll talk about how to calculate the inverse. So in this set of notes, we introduced the idea of an inverse, focusing on square matrices. We talked about how some square matrices are not invertible. We talked about a bunch of conditions that are needed, necessary conditions, and some sufficient conditions for when an inverse exists. And we talked about the importance of this inverse existing in the context of solving AX equal to B. So if the inverse exists, we just take A inverse and left multiply onto the B matrix or B vector, and bam, we've got our solution. So it should be no surprise that there will be times when we want to find this inverse matrix. For simple ones, we can do it by hand. For more complicated ones, we might have to resort to a computer. But how does a computer do that? Remember, you may end up being the person figuring out how to write code for that. So you ought to know roughly how it's done. And that's what we'll talk about in the next set of notes.